Okay, so I'm going to talk about um, the state of distributed data science in Python, the libraries and tools we have available to us, why it matters, and then choosing between the different tools, hopefully so that we can use the simplest solution for our various use cases. So, why? Well, the why not just use pandas, right? So the creator of pandas himself actually wrote an article titled 10 Things I Hate About Pandas. And among these things, quite notably, is the eager evaluation model, which I'll talk about in a second, and then limited when it comes to multi-core algorithms and its management of RAM and things like this. And then complex grouping operations are awkward and slow. We'll talk about that. And then I think this one is really obvious, and I've run into it, and I'm sure everyone's run into it a ton of times. That is, appending data to a data frame is tedious and very costly. And yeah, it is really costly. If you ever append things in a loop, it costs a lot. So you probably want to do like a list of dictionaries and then cast it at the end. So Pandas is a great package for data manipulation, but I think it's quite ironic that it's fairly limited when the data sets themselves become more demanding and as they become larger. Okay, so what can we do? Well, a few solutions exist to address some of these shortcomings of pandas directly. A lot of these solutions tend to focus on adding computation and execution logic to allow the operations themselves to scale. So, what I mean by this is that they'll add some things such as out of core algorithms. And what out of core algorithms are, they're also called external memory algorithms, but they allow us to process data sets which are actually too large to be loaded entirely into RAM. So, what they do is they come up with some efficient system that involves chunking the data from disk and loading it in and out of disk store as necessary and doing computations that way. Another key functionality that these libraries will add is lazy computation. So this directly addresses one of the comments made by the creator of Pandas about eager evaluation. So lazy evaluation or lazy computation involves declaring a sequence of computations, and then later the user is actually going to ask for them to be computed in a chain at once. And why does this matter? So this way of thinking allows for the underlying framework to construct a computation graph, and then once it has an idea, okay, these are all the operations that I'm going to have to perform on this data, chained together in some graph structure. We can then think about how we can optimize that computation itself, making it far more efficient. So you can imagine, perhaps I don't have to create copies of things and pass copies around, which will take forever. Instead, since I know I'm chaining these operations, I can mutate them in place, things like this. So frameworks that use lazy evaluation attempt to leverage as much as of the hardware resources as they can, and they are really going to excel on large data sets. Okay, the last one we can talk about is distributed task scheduling. So distributed task scheduling would mean that, let's say we have the ability to perform computation on lots of different CPUs. So whether that is cores or potentially GPUs, but we have different computing units themselves, and we can schedule a task for each one to execute. And then a lot of times these frameworks, okay, that's great, but the key feature is that they will handle aggregating those results from all the independent processes, and they'll aggregate those things together for us. All right. So implementations. So there are a lot of distributed computation packages out there. Um, But one aside I want to make right now, and we're going to circle back to this, is that distributed computation shouldn't be confused with parallelization. So parallelization is a lower level concept, and it's less concerned with the sharing of data amongst all the processes, and loosely will typically refer to the launching of independent processes at the operating system level. Okay, meaning the the CPU can be executing code at simultaneously or near simultaneously, right, on different CPU cores, and they're just these processes are running independent of each other. Okay, they don't know about the state of each other and things like this. So when you launch a thread, so if you come from a language that's not Python, a lot of languages, especially a compiled language like C, C++, things like this, you typically think that, oh, I launch a thread and everything is going to run, we're going to have two processes and everything will be hunky dory and we can have thread locks and things like this. If you're familiar with MPI, OpenMP, things like this, shared data, and we can just make a distributed version of my loop and it'll all be great. Well, you see, the problem in Python is that it actually can't create a OS level thread. It all exists in the same Python runtime, as they call it. And so you maybe feel the code may be executing in a way that's simultaneous. Um, from the programmer's perspective, I mean, in reality, it's, you know, not precisely simultaneous, but uh, colloquially, okay, let's just say the code is executing simultaneously. However, they're all existing within the same Python process, the same Python runtime, which means that what you don't get is the ability to use more CPU cores, to use more computing power. So what you get from this is, well, in Python, you can use threads to have things execute simultaneously, which would be which is good for most applications, but if you're launching the thread less for simultaneity and more to leverage CPU power, you don't get any of that. So we're going to circle back to talking more about that, the solutions that exist and things like that, because Python kind of does have, well, it does straight up have a built-in solution for this. But let's talk about distributed data science packages. And these are specifically distributed data science packages. They are not focused on overcoming the whole threading limitations of Python. So the first one would be Dask. Okay, so Dask really what it's after is it's providing its own implementations of pandas and numpy data structures, and they kind of have their own naming system. They call them like Dask bags, for example. But the primary idea for Dask is to speed up computation of pretty standard pandas operations, specifically on very large data sets, and it does this by using shared memory, task scheduling, and lazy computation. So immediately we notice, okay, well, we have the whole shared memory component and the lazy computation component. That goes beyond this idea of launching separate processes just to use more computing power. And that's really the core concept of Dask is that it's designed for just very large data sets um, that would greatly benefit from using, the cores in your laptop at your disposal. So the other thing I will say is with their built-in own implementations of Pandas data structures, it is quite approachable, it's quite easy to use, and it will definitely speed up your code if it's on a sufficiently large enough data set. So if we see an example here, if you have a data frame, you just read the CSV, and then you can group it by something, then you can uh, do a mean aggregation. Okay, fine. In Dask, the only thing that you change is actually instead of import pandas as PD, you just import dask.dataframe as DD. You pretty much go everything normally. And then the only thing to note is you call this compute. So remember, it's creating a computation graph. So in this so-called graph, and again, that's just a sequence of operations that the framework knows it's about to apply to something. So we say, okay, we're going to do a grouping operation, then we're going to do a mean operation, and these things are all getting added to this so-called graph. And this whole time, Dask is figuring out, okay, how am I going to actually perform this operation in a very efficient manner? What parts of this operation can I distribute amongst CPU cores and various things like this? For example, if I'm doing a grouping operation and then I'm aggregating each group using a mean, well, you can imagine that um, after the grouping, this whole mean aggregation, this is going to happen independently for each group that we created, which means that we can actually um, leverage the CPU cores that we have available to us and execute the aggregation on all of the cores independently and then aggregate them together at the end. So if you do something like this, and then you say, hey, okay, I'm ready to actually get it done, and you say dot compute, well, um, Dask is smart, and Dask will make this operation much, much faster. Okay, so what do you actually need to use Dask for? Well, they have actually a pretty useful little bullet point list that talks about uses and anti-uses, but I will do my best to try to boil that down, as well as I personally understand it, which admittedly is not as complete as I'd like it to be. However, the gist of it seems to be that if you have very large data sets and you'd like to run fairly standard pandas computations on them, and either the dataset does not fit into RAM in one chunk, or you have a lot of cores on your machine, or just more than one, I suppose, that pandas can't leverage because pandas is just going to run, and that one Python process is going to run on one of your cores. So again, really, Dask is going to be great for the large data sets and chaining a bunch of operations together that you can just that can be parallelized. So what shouldn't you use it for? Well, this is all coming from the documentation of Dask, but if your data set is going to fit into RAM and it's not really pushing your limits there, then it's probably not big enough to benefit from Daska's framework. Um, or if you need pandas operations that are beyond the core functionality, this is something that I've noticed. So, pandas is a very big library and it has a lot of features. Dask, they're trying to do a lot of things and they're not really able to port every pandas feature over into a parallelized, distributed execution framework. So really what they're going to support is rolling operations, grouping operations, resampling operations, and element selection or masking. So that would be masking rows, columns, things like this. Those will really speed up with Dask. However, some things won't. So grouping and merging operations on things that aren't the index of the data frame will not benefit, which I suppose kind of makes sense because Dask is going to arrange data in a certain way, and that's going to be based on the index itself, right? And if you do things on the columns, then it's not really built to be able to parallelize that well just by the nature of the operation itself. So if you want to use more of your available resources, so the cores in your CPU, to perform just independent operations. So, for example, if I had a script and I want to run that script on 10 different data sets, I don't have to, let's just say it's something simple, okay? It's going to take each data set, it's going to perform some computation, and then let's say it just saves the computation results to some CSV file, okay? Well, let's say I just go to the command line and I go Python, main.py, and then, dataset one. And then I do Python main.py dataset two, things like this. Well, since each of those script runs that I'm doing are just entirely independent operations and they don't seem to have anything to do with each other, it doesn't really seem to make sense to use Dask for that. And we'll get into, a little bit more on that later. Because Dask is centered around sharing memory to perform calculations that leverages task scheduling and a computation graph. So you're not going to use a computation graph when you're just running that script over and over. Um, you're just performing, single operations on each of those data sets or whatever it may be. And then Dask does provide schedulers, including a multi-proc scheduler, which would allow tasks to use more CPU cores, and I'll talk about that in a minute. But it's not to say that Dask wouldn't help here, okay? Because what it would help with is um, you could take that Python script and you could have it use Dask if each of those 10 data sets was quite big, and then each of those individual runs themselves would be quite fast. And they would be faster. And so if you're running them in serial, you're running a loop and you just loop over all 10 data sets. Then each iteration of that loop itself would be faster. Um, but that's something to think about because if you still don't satisfy these criterion of, your data sets aren't really that big and, you're using grouping and merging or more complex pandas operations that are not really supported in Dask, then perhaps Dask, doesn't really fit the bill. Okay, so we'll take a brief look um, at their architecture. So this is kind of what we already mentioned. Um, they have these collections that are again mimicking functionality from NumPy and Pandas. They have the Dask array, that's like a NumPy array, the Dask data frame, like a Pandas data frame, et cetera, et cetera, et cetera. Delayed for delaying computations, but you wouldn't, I guess, interact with that directly. So what you would do is you'd use one of these collections, then you'd define those operations to perform on it, exactly like the example that we discussed before. So we have a Dask data frame, we define a group by and then a mean, and then the task graph can then be constructed from those operations. And then we call .compute, and that's where these schedulers are going to come in, and they're going to handle executing these things if we'll just talk about a single machine for now. If you're on a single machine, it's going to handle executing these things in the most efficient way by leveraging, the processes um, that it could spin up, the multi-process library, the different threads it can use and things like this, and it's going to aggregate them accordingly and, do all that fun stuff. Okay, so that's Dask. Quickly about Ray. I'm not going to talk too much here, so Ray is large. Okay, it is large. It is a large toolkit that has a ton of different um, little subcomponents, but it's focused on distributed computation specifically across machines and specifically for machine learning applications. That does not mean it can't run locally. I've used Dask and Ray, but I've used Ray the most even just locally on a machine because truthfully, what's the difference if the CPU cores um, are on my machine and you already support across machines, then, which is a far more difficult problem than they also support, just on your own machine. So a couple of these components, RayTune is for distributed model training, Ray datasets, distributed data processing. Um, I made a typo here that should say Ray Train. Um, Distributed model training. RayTune is for hyperparameter tuning. Um, RLlib, that's potentially, that's an extremely popular library and pretty much the standard for doing reinforcement learning in Ray. And reinforcement learning is very computationally expensive. And what Ray lets us do with really all of these things is sharing memory across different worker nodes. And the worker nodes can conveniently be locally on a machine or across several machines. And so if that shared memory is a very important thing, right, to avoid copying to several processes and things like this, then Ray will solve that and it will solve that blazingly fast. Um, so Ray is really targeting a quite a complex problem. This complex problem uh, is centered around scaling across disparate machines, even just independent machines, sharing memory between them, and doing some, really complex load balancing, task scheduling, and tons of just, feature crazy HPC type things, where, you know, nodes can manage their own load balancing. Then there's, we can load balance across nodes, all these different things. Um, Ray is also probably the fastest solution when it comes to this, but it's definitely going to require the most work to migrate over to it. And again, it's just so complex but also comprehensive that it automates less of the process, which makes it feel like you're maybe getting into the weeds a little bit and you're operating a little bit lower level. Okay, the good news about Ray is that, well, I personally have used it quite a bit. And the nice thing about it is you pretty much don't have to ask yourself lots of questions about, oh, what kind of operations does it support? Like you kind of ask with Dask, and then maybe questions about sharing memory and things like this, because it will do it just for you. Um, and if in the previous example, let's say I had to launch, um, you know, that Python script on a bunch of data sets, well, I can just tell Ray that these are all the jobs I want to execute, and it will just handle it. It'll parallelize it across everything that you need. You can set up all different types of things, rules about what resources to use, and things like this. And then, at the end of things, you can even just handle the aggregation yourself somehow. Again, that's probably not the most fun time, but it works. And sometimes, with Ray, well, the my attitude seems to be it's just going to do whatever you need it to do. And I should say it's not too complicated. I mean, it's not the most complicated thing I've ever seen. It's just not as simple as, import das.data frame as DD. It's a little bit more than that. However, uh, I mean, sometimes it does feel like if you're going to use Ray, it's possible that you're kind of, shooting a squirrel with a hand grenade or something like that. I don't know. But something powerful for sure. Something a little bit overkill potentially. Okay, so then comes Modin, and Modin's an interesting one for sure. So what Modin does is it gives us a layer of abstraction that's actually on top of Ray and Dask, where Ray and Dask are both backends that are available to you through this Modin level of abstraction. And then you can just choose which backend you want to use. It's attempting to be a unified drop-in replacement for pandas that's using Ray and using Dask. So Dask in and of itself is supposed to be a drop-in for pandas. Modin is designed to feel the same way and then also just support multiple backends. Ray, of course, you can make decisions about what backends it used for any like several different parts of the underlying computation process. So a lot of configurability through Ray, and then Modin just is going to give you a little bit more. Um, Okay, so Modin seems like a great choice. There are other ones. There's VA Vakes. I don't know how to say that. That's built on top of Rapids, which is a whole toolkit. And then there's QD. Oh no, sorry. There's QDF. That one's its whole kind of built on top of Rapids, and that one's focused on GPU computation. But these five are probably the most popular you're going to see. And then, does Modin really count? I mean, I guess, but it again just lays on top of Dask and Ray. So there's that. But here comes what I think is potentially the most important question, which is this really what you want? And I think that's definitely an important question to ask when we're attacking a problem. So here are some questions that you might want to think about. So if our data set is going to fit into memory, then adding in the complexity of a framework could very well cost more time than it actually saves us. We already know that if it fits into memory, um, and the operations we're performing are we've thought through them and we're not passing around copies needlessly and things like this. If we just kind of optimize a little bit of our pandas operations, then adding in a framework on top of it, that might not really help. Because remember, these libraries that we're talking about, I'm specifically referring to them as distributed data science libraries. So they're really focused on just having big data sets that will benefit from memory sharing across lots of different things. So what you might want is multi-processing in Python, and we'll talk about that in a moment. But I have a really cool one to share, and that is if you have simple rolling or grouping operations, but unfortunately not resample. You can see there's a GitHub issue for that. It doesn't support resample, but rolling or grouping operations, then you can use this thing called Pandarellel, or however you say it. It's impossible to say. This thing is fascinating, okay? It is it is dead simple. So all it does is it allows some user to parallelize simple operations, specifically rolling, map, or grouping, and that is it. Rolling, map, or grouping operations across one local machine's CPU core. So this does not worry about distributing across many nodes. It doesn't worry about doing this whole memory sharing thing and stuff like that. No. Um, rolling, mapping, grouping operations, as we talked about with Dask, you can imagine they're pretty trivial to just parallelize. You form your groups, and then you can just have a bunch of processes perform the actual computation on each group themselves, and then come back and aggregate it. And it's just a simple way to parallelize. It's a simple problem. So it's literally featureless. That is just it. That's all it does. It will parallelize those three things. It's very, very simple to use, and it just works. It's fast to make it work. It's fast when it runs, and it's incredibly convenient. If you just wanted to do, one of these, let's say, grouping operations on a lot of data. Um, so I'll just give a quick example before I talk about the implementation. So literally, if you were to do my data frame dot apply some function, all you do in Pandarellel is you just replace this line. Instead of dot apply, you do dot parallel apply. That's it. That's all it does. And it'll distribute that across all your cores and aggregate it for you and give you the same result that apply would, but it uses all your cores and it does it way, 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 way faster. And that's it. That's that's all. That's it. So again, super convenient. So literally all it does is it's going to take these pandas operations and then it's going to use a built-in library, which is the multi-processing library in Python, to actually perform that computation, let's say on each of the groups if you're doing a group by. It then just pickles the results, it serializes them, dumps them out to some temporary files, and then it'll take those temporary files, load them back, and then it'll aggregate it for you and just give you the result. It is actually one Python script. That's it. It's just one single 500-line Python script on GitHub. That's all it does. It has 3,000 stars, and it's good, it works, and it's convenient. So if you had an expensive grouping operation and that's all you needed to do, I would just, use this. You just drop it in and you just do parallel group by, parallel apply, or whatever it is. Um, and it just does it for you. So, okay, so it uses the multiprocessing library. So this is important to talk about for a couple of reasons. So let's say that you had to do some operations that are a little bit more complicated, right, than just a one line parallel apply, parallel group by, something like this. Well, Python, we discussed before, its threads actually won't let you leverage those extra that extra compute power you have on your computer. It won't actually let you create CPU or OS level threads. Okay, so that's a problem. And this is called the global interpreter lock, as they say, of Python. So the GIL, you hear that thrown around a lot. That just means Python threads are not OS threads. Python threads will give you the ability to execute code simultaneously, but not execute code on several processes or several cores of your machine. So it's actually simple, and it's a good fit. It's built into Python, and it's a pretty good fit for some problems. So, for example, if I was doing that 10 dataset loop that I referred to before, what I would do is probably not just go to any of these libraries. I'd actually just use Python's multiprocessing library and then just have it launch one process, like for each dataset, and then that's kind of it. And then it will just do that. Um, However, if you needed to share memory between the processes, no, use something else, right? You need to use one of those distributed data science packages that we talked about before, like Modin. And then one other thing to mention is that each process involves starting a whole new instance of the Python runtime and was going to just re-execute everything in your script. So because you're going to start a new instance of Python, that's a considerable amount of overhead. But that's just caused by that limitation of Python's global interpreter lock. So what exactly am I talking about? Well, if you imagine that first, let's say, cell of your Jupyter notebook that you run, where you do a bunch of imports, maybe you read some data from disk, something like that. It does take a second just to run that. And you can imagine that, if you open your notebook, the Python runtime actually just already started, by VS Code or by, whatever it is that you launched your notebook with. So if you combine the the second or two it took to start that Python process with the second or two it took to import those various libraries with the 5 seconds it took to read in that data frame, well, let's say that each of those 10 processes had to load the some piece of data that they all use for something. So let's say they all load the S&P 500 closing prices. Well, it's going to be loaded 10 times in 10 processes every single time. And on top of that, it's going to take a couple of seconds to stand up each process. And once that script finishes, it's just done. So it's not kept alive by the operating system and can be reused. Unfortunately, if you're looping and then you start a new process, well, it happens all over again. So there will be some overhead, and then depending on the script itself, this is one of those things where it's just you kind of just have to be experienced with it. You kind of just have to know. But the programmer themselves will have to evaluate how much overhead is there actually going to be introduced by launching a whole new Python process every single time, um, and is it going to be worth it? The other thing to note is that this is lower level than the other options. That doesn't, it's going to be a very manual process here. You're going to have to tell Python, hey, launch a process and execute this code, okay? And then collect the results, doing it this way, and then aggregate the results, like this, for example. So I think that's a legitimate complaint. However, on the other hand, I've used it quite a bit and the API, I think, is pretty simple. It just gives you like a handful of operations. It really doesn't involve learning a bunch of stuff. And I really don't think it's that big of a deal. But if you need anything that's beyond very simple aggregation of results, or you the overhead of your processes is considerable and there's a lot of repeated computation that would be performed by launching a whole new process every time and re-executing the whole script, um, then it's probably not for you. Because if your aggregation is a little bit complicated, then you're going to have to manually code how those results are merged together. And then the difficulty of doing that step is going to be entirely dependent on how complicated that aggregation logic is itself. Most of the time, I don't think the aggregation is typically going to be that complicated. But if it is, then use something else. And that's kind of the moral of the story, when it comes to the state of these things. So, you know, it's important to note, of course, that the different. I mean, there's different even within Python. There's different options for multiprocessing. There is the built-in library. There's some other things out there, like IPyParallel, which is focused on IPython, and it's going to use a C backend with MPI and things like this. I've looked into these, and again, this is just for multiprocessing, not for distributed type data science stuff with all sorts of, we'll handle splitting up your data set for you. We'll handle, you know, um, load balancing all the cores and splitting up, your grouping operations for you, things like that. Um, this is just for launching a bunch of processes. And IPyParallel seems kind of good, but to be honest, it still looks a little bit manual to me. I've never used it, but it looks like a pretty manual endeavor where you have to set up the task scheduler and things like this manually. So that's kind of the state of things for just launching a bunch of processes. I reach for multiprocessing, the built-in multiprocessing library in Python. And again, I haven't found my aggregation situation to be that big of a deal, especially if I'm just looping, let's say, a compute a factor for every column of a data frame, or maybe for every price series in a CSV on my disk. Then it's not really a big deal. And multiprocessing will give me a big, big, big speed up on that, especially just because I have a ton of cores and I don't need to worry too much about memory efficiency. I have a bunch of RAM, I have a bunch of cores. Um, it's not really a big deal. However, if the data set itself is quite big, or perhaps you can combine, let's say, all those different things that you need to do the computation into one big data frame, then, offloading that whole distributed logic to one of these distributed data science packages would probably be a good idea. So I would say that for launching a bunch of processes, there are two things I consider. I would either reach for Python's multiprocessing library, or I reach for Ray, and Ray will handle, the load balancing, the launching, all those things itself, and it's a little bit less manual there. The other thing that's nice about Ray is once you kind of know how to do that, then you also have the knowledge to use their hyperparameter tuning frameworks, and things like this. And so you can tune a bunch of parameters, by running a bunch of trials on all the CPUs in your computer. And so that's an example of a type of operation that is able to be distributed and then aggregated and then distributed again. Because let's say that you launch, 20 trials with 20 different hyperparameter combinations. Those will all run at once, and then they can all kind of report those results back to Ray, and then Ray can make a decision about what batch to spit out next. Ray is also it also doesn't do this, um, e- exactly like that. It's not going to wait for all of them to finish. It has a pretty clever way of doing it online, where as they finish and report back, it already knows. It just updates its next best guess for a trial, and it can just dispatch it and run it again. And that's not really something that you would be doing in multiprocessing manually. So that's an advantage for Ray. And then if I was able to combine all those things into one data frame with, more or less standard pandas type operations. Dask, or it's really the same thing, I suppose. Modin is probably what I'd be reaching for. Modin, pretty straightforward. Just like Dask, you just import, I don't know, like modin dot data frame as, whatever. And then you could just kind of go about your life. If you're able to do it that way, where you just have one big data set and you can chain operations together, then something like Modin is definitely going to be a huge bang for your buck, and it's going to make that computation very, very fast. Um, so yeah, so that's kind of the state of things. That's how I choose between them. And then I guess the only other thing to do now is to give some code examples, which I can definitely do. But that's a summary.